course, I will finish this part and just making some notes on what we have last week, and we will have an assignment, okay, for this Thursday assignment. Please check your Moodle later on the Thursday. Probably you have around 3 to 4 days to complete the assignment. Okay. So no need to come to class on Thursday. Okay. So last time we discussed on the it's still in the principle of polymerization. This is about the functional group reactivity and molecular size. So, as I mentioned before, okay, that the chemical reactions on the polymers, it is because of the collisions of the functional groups that is reactive. Okay. And because of that, we will have the polymerizations, okay? And then the reactivity itself, it depends on how much the functional group will collide. Like you can imagine, the functional groups will move to another functional group that is reactive, and they will react. Okay? And how frequently they are going to interact, that will depend on how much reactions will take. Okay? And then we can also think, okay, and this is, if we think that if we increase the molecular size, okay, and then the diffusion will decrease, and we thought, if we just take our regular approach, and we will have a time interval between the encounters. But in polymers, the molecular size will not depend, or it will not affect the reactions. Okay. So let me go right here. But it is not really affected. Okay. Rather, the reactivity itself on the functional groups, okay, it's independent, okay, independent of molecular size. Okay. So at the beginning, perhaps the molecular size will give effect, but eventually it is not. So it is only depends on the reactivity. Okay. And later, we are going to see why this reactivity really independent. When we see the characters equation, how we can build up equations, and it is not depends on the molecular size. So if we know the reactivity between two molecules, like you have monomers A, you have monomers B, if you know the reactivity between those two, we can predict how can we make like how high the percentage will be, okay, if we know the reactivity. Okay, and then start with this principle, Fleury principle. If you want to search, you can search a Fleury principle. I think you can try to look up like I mentioned before, the macrogaleria. Okay, that's really nice introductions on the polymer. Macrogaleria. Okay, this is a free website that I think most of some professors, they like build up this website for free, so that you for every level, like from the beginners that really don't know about polymers, and until some maybe high school or maybe university students that they know something about polymers, they can also take this as their reference. and it's really good reference. And I really encourage you to take a look. And sometimes I will take some of my contents from this website. Okay, so the floor principle says that assuming that the intrinsic reactivity, meaning the reactivity within the functional group, is independent and unaffected by the reaction of other functional groups in the molecule of the monomer from which it is derived. Okay, so that is the floor principle. That is the reactivity of functional groups will be equal. Okay? And we are going to see that in the synthesis, how the step growth can be synthesized using this principle. Okay. Equal reactivity, we can also approach the equal reactivity through this, can be approached through stoichiometry. Okay. Stoichiometry balance. Okay. And then here's just a small problem. I think we end up until here last time. If you see the questions, look up the questions. Let me read it for you. So polymerization of phenyl chloride, okay, produces polyphenyl chloride, or we say this is a PVC, of high molar mass at low, okay, at low monomer conversions. This is important. Where the other polymers, polymerization is ethylene glycol, is the normal alcohols with the terephthalic acid. Okay, and it produces the polyethylene terephthalate of high molar mass. Okay, high molar mass only at very high conversions. Okay, that's all a clue. Okay, a clue. And you need to keep in mind when we deal with this polymer synthesis, low monomer conversion, and this is very high conversions. Okay. Very high conversion of the functional groups, the alcohol and the carboxylic acid, right? The acid groups. Okay. And see entry here. I give you the entries 6 and 9 to see the structure. So as you may see, this is the first one. Phenyl chloride. It says it's the low monomer conversions. Okay, that is producing the PVC. Okay, and this is, I believe, will give you a brief intro on how we can at least differentiate, okay, from the structure. So if we see the phenyl chloride, we see the double bonds, right? We see the double bonds here. But when it turns out to be at the polymer, it's pretty similar. But we lost the double bond, which means that it breaks out and somehow it's chained with another phenyl chloride and with N numbers. Okay, so it's become polymers. But the second one here, we have a two substances. Okay. We have the alcohols, okay, the ethylene glycol. So see that we have two alcohol groups. Okay? Two alcohol. This is a difunctional monomer. And then we have the acid. The acid is having this aromatic group in the center. But the important thing is the functional groups. Okay? So when we first learn about polymers, like at the previous slide, I'm telling you that the molecular size for the reaction itself is not as significant as the functional groups. Okay? So as we take further studies, we will see that if we can take these functional groups, okay, and we can maybe decide which one is to react to the other one. Okay? And how we decide that is because of the unpaired electrons. I will tell you later on this the synthesis. But see these two differences. Okay? And then this alcohols and the acid, it's reacted, and somehow, okay, this is part of the alcohols, this is part of the acid, right? So there is something that is reacted, okay, and for obvious reason, that is the functional group. Okay. Now, the question for this problem, okay, for just the introduction, for each polymerization, explain what the observations indicate in terms of the type of the polymerization taking place. So it is asking all of you to decide what kind of polymerizations for each one of them. Let me give you the clue, okay? So to introduce, we have the step growth, as I mentioned before. We have this method, and then we have the chain growth. Okay. Okay. So for the final chloride becoming PVC, is it step growth or chain growth? What do you think? What do you think? Step? This one step? Anyone? Anyone else? Okay. So this means this is chain growth. Okay, remember, the short idea that I give you, well, it's not really a good definition, but I give you the definition. For the chain growth, usually it is done within a really short time, a really short time, which means that we have, I think I give you the picture, like we have the molecules, the monomers, and we have the initiators. Okay? Remember that. So chain growth, let me write here. It needs to be have usually some initiators, and we have the monomers or the molecules, right? While the step growth, it takes time, slowly, compared with the chain growth. So the step growth, you need to have two different monomers, right? Two different monomers. So from this, just this definition, I haven't write other characteristics, but from these two definitions, which one having two monomers? Final chloride or this ethylene glycol and terephthalic acid? Which one having two monomers? This is just one, right? So two monomers, this one. So this will be the step growth, okay, the step growth. So this is step growth. And this will be the chain growth. You can think the chain growth and step growth like the chain growth like immediately when it's react where something happened with this bond. Eventually that's because some attacks from the initiator. It would create some, we call the it has the unpaired electron. Let's say the electronegativity is increasing, so that's why it will be chain with itself more and more, like in a really short time. But here, you first interact with this, and between this alcohol and this acid, the carbon here, definitely there will be something. Okay, one done, and then another one, okay, then it takes slowly. Okay? And then another characteristic that defines this chain group and step growth is at the beginning of the questions, the final chloride has low conversion. So please remember, the chain growth, it needs only low conversion for monomer conversions. Okay? So it needs low monomer conversion. While in the step growth, it's high monomer conversion. We will see later. Okay? We will see later. This is just like an introduction. Do I still have? Oh, I have one slide more. I think this is the explanations. Okay. Okay. This is if you want to know like before final chloride, it is actually from here, okay? From the acetylene, and then react with the acid. Actually, the invention is because of the incident, but then they found something we call the final chloride, and then they try to manipulate the final chloride until they can make the PVC. And this is the step polymerizations. Okay. We will see more details for the step, okay, in a new presentation. Okay. We are focused now on the step polymerizations. Okay. So today we'll be focusing more on step polymerization. Hopefully, I can at least finish most of the basic example of the step polymerization, because most of the high performance polymers, they are the step group polymerizations, like the polyester, the polycarbonate, and so on. They are step group. Okay. Okay. Now I need to switch to the other slides. Okay. This. Okay. So introduction to polymer system. Now this is our agenda. So first we are going to see the definition, the basic introductions, and then the example. Okay, the basic example of the step polymerization, and then the theory. We call this the characters theory. Actually, there is one more about kinetics, but I think I will skip that for now. I will focus more on the example, the synthesis, and the theory, and characters theory. This is the how to make out the molecular weight, to predict molecular weight. And then finally, this is actually this is summary. What we can do to achieve the step polymerization process, what's in the real practice. Okay? Now, if we see from the first one, okay, step polymerization. So, in step polymerization, it's going to be, it has like a successive reaction. Successive reaction means the reactions will have like one reaction, and then the second one, and the third one, and sometimes maybe it takes some time, and then it has repetitions until they polymerize. Okay? All the monomers polymerize. Okay? And then the other keyword is the reactive functional groups. Okay? Reactive functional groups. That how we can get the functional groups? They are typically from the monomers. Okay? From the monomers. So if you have two monomers. Then the monomers, like let's say monomers A, you need to have some specific functional group, and monomers B also have a specific functional groups. Okay? And then in these polymerizations, in the step polymerization, we have at least two main ideas. Okay? The first one we call the condensation or polycondensation. The second one is addition. Okay? We will see what's the difference later. For the definition like this, okay, in my class, you don't need to write all the notes. Just write the keywords. Okay? I think if you understand and you write the keywords, I hope you can, like, usually in some courses, if the professor or if the teacher they ask you something, you don't need to write it the same as the textbook. You just write the same meaning, not entirely the same, but it's the same meaning. It's what I need. Okay? So you don't need to write all the things like very similar. So I hope you understand. Okay? I hope you understand. I hope you understand. That's more important than the note itself. Okay, this is some of the polymers that we are going to discuss, but I think not all. I think just the polyester, the polycarbonate, the polyamide, that's the nylon, the polyurethane. I think that's also very wide polymers that we can see and we can use. Okay, now let me write something on this of step growth. So step growth, let me write step growth characteristic. So first, that is the functional group. Are within the backbone of polymer chain. And then let me write with the, I think, red color. And then functional groups this is originate from linkage reaction of two monomer units. Let's say AB bond. Okay. It means that maybe you have AA and then BB and then just make AB. Okay. And then let me write the blue. Let me write functional group as F. Okay. F group, functional groups. This will allow for tailoring property, which means it can adjust. Okay. Tailoring property very well. And then most high performance polymer. They are synthesized by the step growth. As you can see, we have the from the top one, polyether, polysulfide, polyester, polycarbonate. All of this is we can see them like I think mostly everywhere, in everyday our life. Okay? And they are mostly based on the step growth polymerization. And then you will see from examples that I will show you I think after this that all these characteristics, all of them are on those examples. You have to have like A, B monomers, monomers types like AA, BB, or A and RB, ARB. Okay, that's also two monomer units. So two monomer units basically says that you need to make at the polymer, at the polymerizations, you need to make the AB bonds. Okay. Okay, now we move to the this idea of step polymerization that depends on the number of functional group present, right? On the monomers molecule. Okay? And as an introduction, consider the linkage formation from reactions the carboxylic acid with hydroxyl groups. So we have the alcohols here, okay? And then we have the acid, the carboxylic acid here, and look at how these alcohols react with this something we call the acidification here, and then it releases the molecule of waters. So release the molecule of waters. So the alcohol here react with this one, or you can say it's the one that is negative is attacking the other one, and then it will makes breaking the bonds and then push the stabilization, and to make stable they are linked together and release the water. Okay. So sometimes for some reactions, like this one, we call this is esterification process, and sometimes it is going to be also give temperature. So we need to increase the temperature. I think around from 80 to 200, around that range, to make sure that we evaporate the water. We evaporate the water. Okay. And then this is just continuations for other part. Okay. If you look here, this also have the same effect or same process. You see the carboxylic group here, and you see the alcohols. So it's also make a linkage between this and this alcohol, and then you can make this and then releasing the water, and then this part can be linked again with the other one. Okay, so link again because it still has the OH at the end, right? So it can be react again until some end. So it can have like a linear chain. So I think we can say that most of what we've done in for today's class, we call them linear step polymerization because the result is a linear chain. Okay, so like I give you example like the noodles. So this is the noodles. Okay, one like long chain. And then let's go for the synthesis. I think I'll wait for a while if you want to take notes. Linear like that. Linear. Okay. Okay. So we call, because before we have this molecules of water, right? That is what we call the condensation or polykondensation. So we condense the molecules or the monomers, and then it's releasing water. That's we call the polykondensation. So every time you see polymerizations, that it resulting in the linear wise chain, and it's releasing in synthesis is releasing some molecules, small molecules. It can be water, it can be HCl or other small molecules. We call those process polycondensation. So when you see any small molecules released, usually water or HCl or other molecules. So we first will deal with this polycondensation type in step polymerization. So step polymerization, we have a condensation, we have addition. Okay, now polycondensation. So first is the polyesters. Okay, can I play this? Wait. Okay, it's moving. I think it's the same aromatic group as previous the dimers, right? And then it goes the alcohols, and then C. It wants to stabilize itself, and it's release. Okay, release. Well, it's a little bit different molecule, but it's the same principle. Okay. Maybe later I will write for you what we have. But this is the polyesters. Let me take one more. Let me check. Okay, let me try one more. Okay, it's coming, and see, it's attacking this one. It's attacking this one. It's attacking the C. Okay, and then stabilize the bonds, and it create we call this is the intermediate substance, and we want to stabilize again, and then release the small molecule, and it's become stable, and later that will be the polymer. Okay. We can also see here. Okay. So as long as we can have the bonds, the carboxylic acid bonds and the alcohol bonds, we could make or we could adjust the reaction. As long as we can esterify, we can make an ester. That's why it's becoming the polyester. And we can adjust, like, we can exchange the groups here. Not only the OH group, we can take, for example, Cl, Br, okay, and then this will be our small molecule here. Can be HCl, HBr, okay. And this is the conclusions, okay, of what we have. Okay. So this is our repeat units. Okay. So it can be typically diols, like 2 alcohols here, and 2 acid, okay. 2 acid and 2 diols. This is also the same structure. Has 2 different N groups, and then 2 alcohol. So the key here is the alcohol. So the alcohol will attack the acid. Okay. So let me explain in a more clear structure. So the polyester synthesis. So first is diol and diacid. Okay. And then plus this is the carboxylic. Okay. Now to give you some context, okay, on the reactions. Oh, what's happened? Oh no. Okay, let me write again. I forgot this is different app, so different shortcut. Okay, now the idea is we are taking these alcohols, okay, and see where does the alcohols have? It has the electron. It has the electron. So it's more electron negativity. It's more high. So this is more negative, right? And from the carboxylic acid, the carbon groups in between the acid and the R is more positive, right? So it's more prone to the attacks. Okay, so it will attack. It will attack that, and it's become unstable, and then we need to stabilize itself. So because there's an electron there, so it wants to stabilize itself, and that's why it needs to break the bond on this double bond. And it's before it has this unpaired electron also, right? And the same thing with the other one here. The carbon group here is also positive, and it's prone to the attack. Okay. And then what's happened is, let me write here, and then it will connect this the diols. It goes inside, and then this is OH, this is OH, this is O. So it has this, still has this electrons. This is also have the electrons here, and to stabilize this alcohol here want to make friends with this one, and this one need to break bonds just to make stable polymers. And that's why the final result and this is the repeat units. And we see that this one here is our ester linkage. So this is the ester. And then the water molecule, of course, it will stoichiometric will be balanced with the repeat units. So it's release water. So release water. And later for the supplement of the content, like the video and so on. I will provide the link. It's actually in the macro gallery. If you want to look, it's on the macro gallery. You can check the polyester, and you will find the video. If you want to also look on the 3D structure, you can also check those websites. They provide you with the structure, and you can, I think you can see 3 dimensions from every angle. Okay, and how do I know this carbon is more positive? It's because of this oxygen, and this oxygen here that is negative, and this is more positive. So if there is another negative, it will attract to the positive one. So it's like suppose that this is a couple, so there's a third person coming, okay, and he take away the couple go away. They separate them, and yeah, and then resulting the water. And similarly, if you change the OH, with Cl, because the electrons have the same number of electrons, it will be the same process. And you can change the OH with Cl or Br, the same groups, right? That has a negative. So let me maybe write with a different color. So this OH can be switched to Cl or Br. And then it will release the HCl or HBr, or depends on the molecules. And where you can find the polyesters? Anyone know or going to guess where you can find? Maybe your clothes? Not sure. This is polyester. You check usually the brands. Usually they will maybe, if this polyester, maybe polyester. In your PET bottle, I think also polyester, right? Yes. Clothing, and although you can see the difference, right? In the bottles, you need to have like more mechanical property, but in clothes, you need to make to be like in a fiber, and the fiber means that it need to be flexible and stretchable. That you need to wear your clothes, right? So you can be in your packaging, in clothing, and in bottles. At least the mechanical property is to withstand or to overcome if there is pressure, right? Like in the carbon dioxide. Okay, I think we can go to the next part. This is for if we need more example, but I think I already mentioned before, so no need. So we can go to the polyamides, or usually we call the trade names the nylon. can see how it goes. It's react, okay? So you see that this is having the unpaired electrons, right? Unpaired electrons. Maybe so unpaired electrons, it will collide with this H, okay? Just small. I forgot to combine with the second one, so let me go for the second one, the second video. So after combining, I have this, okay, and then here comes the nitrogen here. So nitrogen attack this and makes the connection between the carbon and the nitrogen. Okay. And then stabilizations, and then see that it's releasing the OH minus and stabilize again, and it's released. Okay. And if you see that they are, oh, I think this is wrong picture, so I think we can skip that. I forgot to pick the new one. So nylon usually it's based on so let's start with the reaction of diamine with the diacid, carboxylic acid, or halides. So we start with the diamine. So we need to make sure that we have the amine group, okay, in both ends of the monomer. Okay. The R can be aromatic, can be aliphatic, can be linear. And then plus the diacid. Okay, and then again the carbon here is positive, right? Because this is negative because of the electrons. So this one here, the carbon, is more positive. That's why it's prone to attack if there's another electrons from outside of those monomer. Or we can say this is more positive, or the electronegativity is low, or electronegativity is positive, but that's wrong definition. But let me just write electronegativity is more positive, and then this one is negative. Okay, I think, do you want to take break or no? Depends on you. You want? Did you want break or no? If you want, maybe we could take break. I think we can break. Okay, back again. Okay. So we have nylon, how to produce nylon. So basically similar from what we have before. So because different polarity, this electrons goes here, it want this carbon to be attracted, and very similar process with the previous one. So it will, like you can imagine, this is going here, and this is going to provide some place for the end to join in. Okay? And then some hydrogen will cut off, and then this OH will cut off to become water. So let me go slightly write the reactions. So we have now here. So let's do NR1, and then this will be N, okay, and still have one hydrogen, and then this will be oh, this is okay. Let me write. And here, okay, see that I have 3 bonds. It means that it's unstable, like the previous one. So it needs time to stabilize. This one needs time to stabilize. So some of the electron will comes down and make a double bond here. Okay, and then oh, where's the OH? Should be still have OH here. Still have OH. Okay. And then, just to give you an idea that these two, this is also the one to cut and then release the water. So these two combined becomes water. Okay. And then, let me write. That this is going to be the important part in these reactions. Plus H2O. Okay. So we could identify the reactions through these groups, the amides. Amide groups. And then for the polymer itself, so imagine that these groups, okay, because we still have the diamine at the end, it can still react and make the same amide groups again here, and it can make a linear long chain polymer with the amide groups at the middle. So probably this will be the final result. So nylon, you remember nylon? We have the with N here that has the amides. Okay. And how we rename the nylon is based on the R1 and R2. So if we have the carbon in R1, the total carbon is 6, and the total carbon in the R2 is 10, that is nylon 610. Or if they get the same carbon, 6,6, we call nylon 6,6. Okay. So this is number of carbon. Carbon, this is number of carbon. In R1, in R2. Well, actually not only R2, but this should be R2 and this 2. So 2 plus R2. Maybe plus 2 plus 2 plus 2. and R2 plus 2. And of course, because this is only releasing the water, so we need to evaporate the water to remove. And this is also can be applied if you change the OH with Cl, like previous polyester. So we can exchange this, can be switched with Cl. Okay. Now the nylon or the polyamides, we write some characteristic. Or maybe before that, let me introduce you to, if we have okay. This is a typical amino acid. Okay. Amino acid. So amino acid has a typical N, H, C, and O, right? And if we can react this and make a self-condensation, we can imagine this will go through and it will repeat itself. Repeat itself. And then this is what we call the protein or the maybe peptide. And of course, it depends on R, what kind of amino acid or the peptide or protein. And it goes a similar way with the reaction on the polyamides in the nylon, very similar. So some property of nylon includes that nylon properties includes the crystallinity, which means it's semi-crystalline. It has a strong hydrogen bond. Good, we could say good mechanical and thermal property, at least for some smaller scale applications. And you can find the example or the applications in clothing or textile, stockings, it is also nylon, yeah, fibers, right? And also in automotive or some engineering process, they need nylon. Okay. Ah, sorry. Ah, it's gone. Right. So my crystalline. Forgot the shortcut. Always mix out with the other apps. Strong hydrogen bond. Mechanical and thermal. It's good. Okay. It's on textiles, stockings, fibers, automotive, engineering, and some. Okay, if you see the previous example, we imagine we take the R, right? We have R1 like that, right? In our polyamides or the nylon. Now, of course, this R is really interesting. Okay? If we can find what kind of R that we want, okay, or what kind of R that we can adjust to make some specific property. So if we imagine this R like a regular nylon, so maybe this is just maybe if this is having a 6 carbon, just a 6 carbon like that, linear, right? And this is another carbon here, and maybe this carbon combining 8 or 10 or 6 is also linear, right? We say it's just an aliphatics means linear, aliphatic polyamides. And when it's linear, the fiber or the nylon is very flexible. You can stretch, right, because it has a long chain. Right? But how if we change this R, for example, with the aromatic, if we have ring, so if this become ring, so imagine switch to aromatics. If we switch to aromatics, this is becoming what we call the aromatic polyamides. Okay. Or sometimes we name with the abbreviations the aramides. Aromatic polyamides. And this is what we have in Kevlar. We have it in Kevlar or Nomex and Kevlar. They use the aromatic polyamides. I think I have the notes after this about the aramides, why it's become really crucial when we change to the aromatics. Maybe anyone wants to guess what's the advantage using the aromatics here? Any guess? Any guess? You can comment with any imagination you have. Rigid? Yeah, yeah. Rigid? Any other comments? Good comments. Rigid? Any other comments? No? Okay, I think let me explain why it's become more rigid. So this is also one of the high performance polymers, which means that the property are really good, and we can adjust and make it more predictable. It means that if we want to mass production, we can mass production easily. Okay. So this is a typical aramid. We have, remember our R1 and R2. So let me also draw here. So This is for, let me maybe using red color. So this is for bulletproof vest, or sometimes you call this with the trade name the Kevlar. Remember, we have the R1 and R2, right? Well, I think I draw the N first and then the C. It's the same thing. Okay. R1, R2. So in this structure, if we see the original one, this is the aliphatic one, and this is the aramids. This is aramids, and this is original polyamids, or the regular. Okay. We can have transposition and cis position. If you remember cis trans in chemistry, you can have like here and then the other one. You can imagine this like flip in this nitrogen here. So see that H becomes in the opposite direction, okay? And then that's why the chain becomes like a coming down here. It's, I think, the problem we have. I think me personally, when learning the cis trans, because we look at the books and the books just showing you two-dimension pictures. It's a problem. If you look three-dimension, I think it's really good. You will see that it is really make an opposite direction. Because if you see here, why is it like it's going down there? If we see the three dimensions, very good. I forgot to pick the 3D picture, but I hope you can try to look out the 3D pictures to give you more understanding. Okay, and then why this important? So in polyamids, they can have these two cis and trans positions. Okay. So in the trans positions, the trans amide, the so let me explain from here. This is just explanation about cis and trans. Let me explain from here. So if we have this, so maybe imagine like it's a long chain. It's really flexible, right? Like really flexible. You can stretch the fiber easily if you have this line like this. Okay? This is the trans position. Okay? This is trans position. So trans, easy, flexible. Okay. So this is trans, and this is cis. Okay. But when you take the cis positions, if you have the linkage of cis, it will mess up. Okay? It will be the stretch is not there. Okay? And the polyamids, they can have these two cis and trans. Okay. Now, to overcome this problem, in the aramids, we exchange with the aromatics. So the R, we exchange with aromatics. These positions, because of these aromatic groups, it will not happen. This will not happen. This cis will not happen because the aromatic is too big. It's really big molecule. So the aromatic groups is making sure that the change is always in trans position. Okay. So aromatic groups ensure the cis position, conformation or position. So that's why in Kevlar's, if you imagine a fiber, you can easily cut from the sides for the fiber, but from the longitudinal side, it has very increasing property. So in Kevlar or in your bulletproof, you can make sure that every polymer, every fiber is on the same direction. So when a bullet comes, it can deflect the bullets. You get the idea? Let me draw for you. So if we make this fiber, okay. So the orientation is on longitudinal. You see the bullets here. Goes there. If we have tensile position, here is the strongest. The bullet come, it will deflect. Okay, that's the theory. Of course, there is some not 100% perfect, but the theory is okay. The theory is okay. So we can deflect the bullet. This is on the Kevlar. This is orientation of the fibers. And then the aromatic makes all this polymer, make sure that all is in cis conformation. Okay, that's the aromatic polyamides. Okay, now the third example. So first polyester, nylon, and now the polycarbonate. Okay, this is natrium hydroxide. They come exchanging the electrons. Okay, exchange the electron, connecting some part, and then release the molecules of water. And it's also the same. Okay, this is you can imagine this like R, like before, like a previous example. Okay, and this is the second one. So another one come and make the reactions and cut and then release the chlorine. And chlorine will take away also the natrium because it's positive and negative and make it salt. Oh. And then also it's attack another one. Attack again the unpaired electron, attack the carbon, make the connection again. Okay. So it's actually pretty similar, right? Oh, just the difference is just this one maybe makes more complicated. But the idea is you can just focus on the functional groups. Okay? Focus on the functional groups. Okay, polycarbonate. Perhaps this will be the last section on today's class, okay, polycarbonate. Let me write So maybe before we write the synthesis, just a note what kind of example we have for polycarbonate. Usually we use the polycarbonate for protection, for like shields, helms, like in your, if you drive with your motorcycle, usually that is polycarbonate, the helm. So it's shields, right? The shatterproof glass, like for protections. DVD is also polycarbonate, but I think no one uses DVD now. All is digital. And then helms. So usually the property is tough and transparent. And how to make? Usually we take the alcohols, the diols, and then why this is so plus this acid, what is it? I think this unpaired electron, and then we have the alcohol. So attack here. This is also negative positive. Okay, electron negativity. Different in polarity. We can also say that. And this break these bonds, right? And then it will react and make this HOROCROH. Oh. Usually, to make polycarbonate, we take the name for the alcohol is the bisphenol A plus phosgene. Okay, and this is, I think, I will make an assignment based on this. So I will have like several questions, and one of the questions is about this bisphenol A and phosgene. Okay. So this, we can say that this is dangerous. So one way to make polycarbonate is this bisphenol A and phosgene. Maybe later you can find what's the reaction and why it's dangerous. And sometimes if you have a little brother or sister, and maybe your parents buy some equipment, and usually equipment for baby having BPA free. That means it's not using any bisphenol A synthesis. Because if you see the usage of the polycarbonate is using for some protections. So if the protection need to be free from toxic, they sometimes using BPA free. And I think one question for you to think is why it's dangerous, this reaction. Because we're using this for baby bottle too. So baby bottle, electric components also. like in your goggles, it's also polycarbonate. So for protection, it's usually transparent. So that's the polycarbonate. Oh, I think we still have time. Let me continue for a while. I think we have okay. Okay. Now this is some of the table that they are all prepared using the polycondensation technique, the technique that we see before. So you see from this one, some aromatic polymers. Some are, all of this is aromatic polymers like the polycarbonate, polyethersulfone. All the reactions, if you see, they have similarity. Okay, they have similarity. For example, they have the N group that have functional groups that will react. Like this K and Cl, they are also going to react. And K, this is also F, they also will react. And these all have difunctional groups in the N groups. Okay. And there will be, I think, at least have an importance. Later I will tell you why they need to have these difunctional groups. And the last one, phenylene terephthalamide. This is fiber. This is for composites. Most of them are moldings and coatings for membranes and some other applications. And still, this is continuation from the previous table. This is also for moldings, so we call this a factra or factra. And it's become more and more complicated, and you see that we can take the aromatic, just one aromatic, single aromatic, or double aromatic. But it depends how we are going to approach our needs, our purpose. And polyimide, and then PBO. This is also a fiber, high modulus fiber. So these are all the high performance aromatic polymer, which means that they are really good in some of their properties. And then the next one, okay, the next one. So we have the polycondensations, okay, and the second one is a polyaddition. So the difference is just it says that the monomers react without elimination of other molecules. We can say that's I think a simple definition of the polyaddition. So polyaddition. So first is the polyurethane. Okay. We have the isocyanate, I think. Oh yeah, another one there. It has the aromatics. But the important thing is this NCO here. That's the important one, the isocyanate. And it will react. It will react with the functional groups that has the alcohols. let me try. Let me play one more again. See the reactions. First, we react the alcohol to take this is an intermediary process, and this is the primary process. So we react this one, and connect it this, and then because that's just intermediary, we don't need that. We need it for just making it connected. Okay. And then see another one. So this is we can say regular polyurethane, but polyurethane itself we can make it as a foam. We call it the polyurethane foam. So the first one, so we have a two process here. So we are going to include water. We are going to include water here. I will explain in detail later. So we include water. Okay. Yeah, and then release the carbon dioxide, and that's why it's become foam, because the carbon dioxide like a bubble, like a bubble. And then we could also have this. Okay. Second process. And then it's becoming become a chain. Okay. So I think I will just stop until here, because I think I need more time for explaining all the details. But we will see you next week from the polyurethane until last page. And there are two, I forgot to mention at the beginning, there are two types of the step polymerization. The linear that we done now, we call all of them linear step polymerization. There are other one that is we call the non-linear. Okay. We will see it later on, the difference, I think next week. Okay, now before we end, let me stop here for a while and go for this, just a small feedbacks. Small feedbacks. Just a small feedbacks. I think very short. Okay, I think we can start. Okay, any comments first? Good so far? Maybe boring? But I hope I can make more interesting in the assignments, so you can work your assignments not as like a homework and oh I need to do this to get a score, but I want to make it more like fun, and you can have more ideas to come. Okay. Tutorials. Okay, tutorials. I think tutorials in our course, because our course is more, I think, more generally in a knowledge information. So, like, for example, like the synthesis, as long as synthesis, you know, like really basic, not in details, I think it should be okay. But if you take polymer chemistry, then that's when you need to know the details. Okay, so far so good. Okay, I think we can go to the next slide. Okay, just a small quiz, and it's really short question, and I hope you still remember. Okay. And I think to start this, you need to use your student ID to help me recognize which one. Okay, I think we have how many? Should be 9. Where is it join? Where is it join? Well, I think it's okay. I will just start anyway. Okay. Okay, just for the almost 50, around 48, 50 seconds. You need to be careful, read the options. Okay, let's see. No one. It should be viscoelastic, not elastic. It should be viscoelastic. Okay. Okay. So no one can. Okay. Get ready. I also forgot the question. What's the question? Yeah. Just we mentioned in class. Okay, 17, 16, 15, 14. You can check your notes. You can check your notes if you write. Okay. Only. So this is actually question. All is step polymerization except one, right? If you remember, I said that in the beginning, the PVC is chain groove, not step. Oh. Right. Okay.
Sorry.
Yeah. Okay. Okay. This is okay. Only one student. Okay. If you have any suggestions, you can write your student ID just to make sure that you take this small quiz. Okay. Okay, if you've done, then class finish. Okay. And if you have time, you can check the macro gallery. Really good website.